Okay, this video shows you how to use the least squares regression line to model a linear relationship between the explanatory variable size of land and response variable price of this bivariate data set here. Part of that is first finding the Pearson's correlation coefficient, R. Now, I've shown you how to do these tables in the video on Pearson's correlation coefficient, so check that out. I haven't repeated it here. So we're starting from this point where we've got R. Now R here of 0.81, positive 0.81, means that it's a strong positive linear association between the two variables, size of land and price of land. Now, the fact that we're actually doing a least squares regression line suggests that we are making an assumption that is a linear relationship. Okay, so also part of all this calculation was also working out the mean of the explanatory variable, mean of response, standard deviation of the explanatory variable, standard deviation of response. So all this is required for finding the least squares regression line. So this is the form of the least squares regression line, y equals a plus bx. Now, that is no different to y equals mx plus c. You've just got to get used to the new letters used. So instead of the coefficient in front of the x is the gradient always, so b replaces m, and the constant by itself is always the y-intercept, so A replaces C. Now, you can also write this equation as C plus mx. Because of the commutative law, you can just swap it around. So that is basically the same form. Okay, you got to get used to this form because it's going to be on the QCAA formula sheet. So I'll just clear those contents. Okay, so this is your equation for the gradient. This long-winded equation here is if you were going to do a table from scratch just to find these two values, but we've actually found the correlation coefficient, so we can use this little formula here and not worry about that at this stage. So I'm just going to go in and say equals R times the standard deviation of the response variable divided by the standard deviation of the explanatory variable, and press enter, and that is our gradient. Now, the y-intercept, I just go and find the mean of the response variable minus the b calculation we have just done, which is why b always has to be calculated first, times the mean of the explanatory variable. So this is our y-intercept. So now we've got those, we can go ahead and write the least squares regression line so that we can model that relationship. So y equals 437,602, that's the y-intercept, plus 1,523.9 times x. So that is our relationship, remembering that y is the sales of the land and x is the area, the meters squared, size of land. Okay, so now that we've got that, that's using the table, using the correlation coefficient to calculate it. We can also work it out using a scatter plot. So I'm going to select our bivariate data set and I'm going to insert a scatter plot. I'm just going to drag that down into this space down here. Just change its name slightly, so I'm just going to say land price versus land size for now. Okay, now if you press on that, you can add a chart element and you go down to trend line. And what you want is linear, and then you can go and select on that and go to this chart and scroll all the way down, display equation on chart. So if you zoom in, you can see that they are the same equation. Remember, the commutative law allows you to swap these two over, which is what I've got here. So now that we've got this line, we can actually interpolate, and any of these values we can put 400 in, 400 meters squared, and we can work out how much we would predict that land to be sold for. Or we can extrapolate, we can go beyond the graph. We might want to know how much land that costs, land of 2,000 meters squared costs, and we can actually extrapolate, extend the graph because it's linear. We can sub 2,000 in for X, and we can find the price.